define so enthalpy. Enthalpy, E-N-T-H-A-L-P-Y. The capital H is the symbol. It's the energy content and have to note it cannot be measured directly. So we cannot just, for example, if we have like propane or we use methane, cooking gas, we cannot just calculate the energy of the methane like that. We have to calculate the energy change when the reaction takes place. So we would know the temperature change. And if we know the temperature change from reactants to products, we can calculate the enthalpy change, which I'm going to show you in the second reaction equation. So enthalpy change, delta H, can be measured, and if it can be measured, this is what we're going to use in the calculation. This is what we can calculate. Enthalpy change of reaction minus total simple equation. Says the total enthalpy of the products minus total enthalpy of the reaction will give you the enthalpy for the reaction. Heat to start. Times the temperature change. This is going to be in joules, this is going to be in grams. Joules per gram per degree Celsius. So specific heat capacity is a constant for a given compound or mixture. And I'm going to define it as we go along. And temperature change in degrees Celsius. The specific heat capacity is the quantity of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So write this definition on the board. Or write it in your book. It's important to know. Right? Is the quantity, so specific heat capacity is the quantity of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. When we are carrying out these reactions and we're making the calculation for enthalpy, we also have to use a container that is insulating, that prevent heat from going in the environment. Like, it will just confine the heat to that container. You know, like a styrofoam cup. Notice that the outside of the cup will not feel hot because the heat that is given off from the reaction mixture will stay in solution. In the world, this reaction will not be perfect. So I'm going to give you some assumptions that we'll make when we're carrying out this reaction in the lab. Because normally, the value that we calculate in the lab is not really accurate, but it's close to the accurate value. Reason being, we normally make some assumptions to enable that this system works. For example, if we calculate the heat change of, say, acid reacting with a base, right? You know that the specific heat capacity that we take into consideration here is actually the specific heat capacity of pure water. But in reality, we don't have pure water. We actually have a sodium hydroxide, say for example, that we're using that as the base, and we have like hydrochloric acid in solution. So in reality, we have to assume that, like, in these dilute solution, the specific heat capacity of that dilute solution is equal to the specific heat capacity of pure water, because that is the value that we're going to use in the reaction. But since these are questions that you can get in the exam, so they ensure that I write them on the board so you can remember them. So assumption. Calculating heat of density is 1 gram cm cube. That is normally when the gram of pure water The density of pure water is 1 gram per cm cube. So if we measure 1 cm cube of pure water, the mass is 1 grams. But if we should measure, in reality, if we measure 1 cm cube of, say, a dilute solution and make it accurate to like 3-4 decimal place, in reality it's not 1 gram. But when we are doing this calculation, we have dilute solution of sulfuric acid, sodium hydroxide. We're going to assume that the density is the same as pure water, because whatever volume we use carrying out those reactions, that is what we're going to use as the mass. So if we use 50 cm cube of a solution of sulfuric acid, we're going to assume that it weighs 50 grams. When we are working the calculation, the questions you will see. Then the 2 specific so have a value of 4.2 degrees Celsius. Alright? Right? So we can ignore the heat that is lost, for example, to the air or to the container, and assume that all the heat that is given out from the reaction is absorbed by, say, for example, the solution mixture, which would be accurately recorded in the thermometer change in temperature. But we know in reality that's not going to be the case. But we have to make those assumptions. So take this from the board because you can actually ask it in the example. Is the heat change You know about solute and solvent? Yeah. Mr. Harding? You know about solute and solvent?
One breathe on the other, I think.
So the solvent is normally like the water, and the solute is normally the liquid or the solid that is dissolving in it. For example, if a salt water, the water would be the solvent, the sodium chloride would be the solute. So notice in the definition we specifically use heat change here because it can actually be release or absorb. So this is just to keep the definition general, so it would entail both exothermic and endothermic processes. Because remember that the heat of solution, dissolving a solid in solution, it can be an exothermic reaction and it can also be an endothermic reaction. So in this definition, we are defining this stuff, we use heat change. Meaning it can be given off or it can be absorbed. The next that we need to know from this syllabus is heat of neutralization. And 1 mole of water is produced in a neutralization reaction between an acid and an alcohol of water. Also look at energy profile and effects of catalyst. Decomposition hydrogen peroxide. It is exothermic times no, remember that when I was talking about energy profile diagram, I specifically state that if you are drawing one for a particular reaction, then you need to, instead of putting reactants on the line, the first line, we should actually put the reactant. So don't write the word reactants there, you put the actual formula for the compound. It's an exothermic reaction. This would be H2O2 aqueous. We're going to produce water here. Yes. Remember that the reaction is H2O2 plus H2O liquid plus O2 gas. we could go 2 here and 2 here, probably balance it. 4, 4, so it's 4, 4. Alright? Now, the catalyst that we use, so this is how we produce oxygen in the lab. We use MnO2. Manganese 4 oxide as the catalyst, MnO2. So you can review that in organic lecture about preparation of oxygen. Manganese oxide is the catalyst. So this would be the energy profile diagram. So here would be the activation energy. Enthalpy change here would equal to minus 98.2 kilojoules per mole. Now, so this is what happened without the catalyst. Now, if we should have add the catalyst, what the catalyst is really doing is it's finding an alternative pathway for the reaction to take place, which normally requires less energy. So it lowers the activation energy for the reaction that is occurring. So a catalyst lowers the activation energy for a particular reaction. So if we note the difference that we would put on this graph in blue, and if I have the reading. Well, I'm not seeing the reading, so we have to work with the blue ink. I'll probably use dotted line. Following? So here, this one, activation energy with catalyst. You're able to see. But just to note that the manganese oxide, in this case, the catalyst, it would lower the activation energy. So this is how you would represent it on an energy profile diagram. So you have to have the enthalpy change, you have to have the actual reactants, the actual products, the physical state. You have to show where the enthalpy change is. So note, the enthalpy change is the difference in energy between the energy level of the reactants and the products.
Enthalpy change is your difference.
Yes. And we are showing the enthalpy change on the graph. Change in enthalpy, you have to extrapolate this line and show that this is the energy difference. Well, activation energy is between the energy level of the reactants and the highest point on the graph, the activation energy. So make a note of the previous diagrams that I drew.